We're coming back on logarithms. Were we in B? I thought we were on... Wait, are we? Wait, have I ever talked about exponential graphs? I swear I have. Alright, let's recap. Let's just see what we remember then. Let's do a bit of a... Whoa! Uh-oh. Must be my girlfriend. I'll read it later. Secretly, I wrote it here myself. I'm like... Sorry? Oh, of course. I'm sure it's... I love you guys. Oh, I'll read it at the end if you guys been good, yeah?
Okay, you probably shouldn't read it, because if there's anything like... Yeah.
Oh. That's a good point. That's a good point. All right, let's recap a couple of things. I'm going to tell her about this tonight. I'll tell her about this tonight. You do know I teach. All right, exponentials. Let's recap. There were 7 laws that you had to go through first. You had to learn your algebra, then you had to learn graphs. There are only 2 things that I need to make sure you knew before moving to logarithms. So, I'll give you law number 1, and then you tell me the rest. Okay, so law number 1, if you have a to the power of something, so let's say a to the power of m, times a to the power of n, so both of them having the same bases,
M plus n.
yes, it'll be equivalent to a to the power of m plus n. So whatever the 2 powers are, if you're multiplying them, you can add them. That was law number 1. Yeah, and I tried to give you the logic, and you didn't have to memorize the rules. Otherwise, you can memorize them. There's like 7 or 8 of them. So, what's law number 2? Oh, give me another rule. Give me another rule, Bruce. What's another one? You didn't write it down. Do you remember anything from the top of your head? I'll give you this one. A to the power of m divided by a to the power of n. What should that equal to, Bruce? A? Not 1. Something else. So if you times them, you add them. Then if you divide them, you would? Good. Write this one down. So it's m take away n. Okay, so if you're dividing them, I'll give you a couple of examples on the side so you feel familiar with it. So let's say you had 3 to the power of 7 times 3 to the power of 8. Then it'll be 3 to the power of 7 plus 8, which you can simplify down to 3 to the power of 15. Okay, if you had division, it would be something like, let's say, 3 to the power of 17 divided by 3 to the power of 2. That's the same thing as saying 3 to the power of 17 take away 2, which is 3 to the power of 15. Okay, so that's what I mean by A being the same base. Base meaning all 3's. Okay? Next one, give me another rule. Ian, give me another one. What else do we know?
0.
Is equal to what? Good, that's correct. A to the power of mn, which means m times n. Okay, so an example would be, let's say I gave you 3 to the power of 7, all to the power of 4. That's the same thing as saying 3 to the power of 7 times 4, which is 3 to the power of 28. Okay, give me another one.
A to the power.
What's another one, Renata?
A to the power of 0
A to the power of 0
equals 1.
equals, fantastic, equals to 1. So we got 4 there now. And I can give you another example. So let's say 3 to the power of 0 is equal to 1. 5 to the power of 0 is equal to 1. 7 to the power of 0 is equal to 1. But 7 times a to the power of 0 is equal to? 7, good. Okay, and it's a common mistake when you do like 3a squared b 2 and then you put a 0 there. A lot of students would see that power of 0 and they say it's equal to 1. It's not. You got to read what it actually is saying. See, this 3 on the outside means multiplication. So what you're really saying is 3 times, and this whole entire bracket here is to the power of 0. So that means this whole entire thing is 1. So that's 3, because 3 times 1 is 3. Okay, so just be careful with that. So yes, while it's a rule, just remember that it's when you have an individual term to the power of 0, then that equals 1. Not the whole thing equals 1. Okay? Okay, so you got 4 rules there. Give me another one. What's another one? Trent, give me another one.
I'm not sure if it's a rule, but like a to the power of 5 is a root function.
Yes, there is a rule to that, but you're right. A to the power of half is the same thing as root of a, and then there was a rule to it so that you know if I gave you a to the power of 3 on 2, what is that equivalent to? What was the rule again?
3 inside.
Yes, so it will become a cubed square root. What if I gave you a to the power of 4 on 5? What does that become? There's a rule for this.
The top number goes in, and the other one, the bottom number goes outside.
So like that? Good. Okay, so the rule, if we just model that, if we follow this last example I had, then it's a to the power of m over n is equivalent to the nth root, that's what the little number outside the root means, nth root of a to the power of m. Okay, so that's the last rule that most students would forget, because the others you learned in year 7 and 8, that one probably in year 10 and you use thirds in year 10. So at that point, most students will forget this one. But 7, 8, these are your common ones. Okay, so this is what you learnt in year 7 and 8, and probably practice a bit in year 9. But that's your common one for year 7, 8. Okay, so you got your 5 rules there. There's still another 2. Give me another 2. Xiang, give me another one. There's something to do with a negative.
A to the power of
Good. So if you have a to the power of negative m, this is equivalent to? Good. 1 over a to the power of m. Okay. So that's your 6. And then your 7th one is pretty much similar to your 3rd one over there. A to the power of m bracket to the power of n. Which is why I don't normally memorize these. I just know it. But what would the last one be? So we've got 7 of them. No square root ones. More fractions now. That's why most students forget it. When it comes to fractions, they're like, oh, I can't do it. What is the rule for this one? Similar to this one. All right, I'll do it. A to the power of m divided by b to the power of n, all to the power of c. What does that equal to? What's this equal to? It's very similar to that 3rd rule. Yeah, good. You're just using exactly the same rule here. It is a to the power of m times c over b to the power of n times c. An example of that, so I'll just zoom in so you can see. I'll zoom in. That rule there, an example of that could be something like this. I'll just rub this off. You could have, let's say, 3 to the power of 5 over 2 to the power of 3, all to the power of 2. That is the same thing as saying 3 to the power of 5 times 2. And this is the same thing as saying 2 to the power of 3 times 2. So what you're really doing is you're doing 2 times the 5 and 2 times the 3. That's what the rule's saying. And so that gives you 3 to the power of 10 and 2 to the power of 6. Okay, and that's as simplified. So that's your 7th one there. Technically, there's 8, just because they varied the 3rd one there as well. I'll show you what I mean by that 8th rule, which you don't need to memorize. You just need to know the 3rd one. If I gave you a to the power of m, b to the power of n, all to the power of c, this is the same thing as writing?
A to the power of n times c times b to the power of n times c.
Yeah, fantastic. It's exactly the same as this one. These two are exactly the same. So it's the same thing as you just said, m times c and b times n times c. So it just becomes a to the power of mc, b to the power of nc. Okay, so there's all your 8 rules there. And really, at the end of the day, you only needed to remember the first 2. 1, 2. If you like, learn the 3rd one. And that one. You should be able to then remember the rest. Most of you will tend to forget these 2, or at least screw up with those 2. Okay, so if anything, probably put emphasis on those 2. Try to recognize those more often. These are the ones you practiced back in year 7 and 8 over here. But over here, this is what you probably want to practice more. Okay, so that's where I left you last term. And then I talked about exponential graphs. and I showed you on GeoGebra how you shift up, down, left, right. So I'm going to quickly revise that and see how we go, yeah? So those are your rules. Remember, exponentials, you have algebra, and then graphs. It's always like that. You learn your algebra to find your x-intercept, y-intercepts, and then you sketch. It's always like the log's going to be the same. You're going to learn algebra, and then you sketch. And there's applications of these. Okay, so let's have a look at exponential graphs now. Let's recap that. Exponential graphs. You have y equals to, let's say, a to the power of, I'll just start off easy. I'll use a number too, so it makes it easy. And remember what 2 to the power of x looks like. What does it look like, Xian? Yeah. Good. It has this sort of slope, an exponential slope, yeah? So this is what it looks like. But there's a couple of properties I want you to tell me. There's only 2 properties, along with a third one that I put in. It's more of a year 12 content, as in to think. This is your exponential graphs. Does anyone remember what the 2 means? If you have 2 to the power of x, so 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. What is that really saying again? Yep. So it goes left to right. It goes up or down. Now, if you think about it, if I drew a table out for you, x, y, if you have, let's say, -1, 0, 1, 2, 3, 4. 2 to the power of 0 is equal to what? 1. And then if we have 1, 2 to the power of 1 is? 2. 2 to the power of 2? 4. 2 to the power of 3? 8. Now, what's the pattern? It went from 1, 2, 4, 8. It's doubling, not squaring. Okay, so square of 8 will give you 64, but double 8 for the next one, 2 to the power of 4 is 16. Double 16, 32. Double 32, 64. Okay, so the pattern is after you go in the positive direction, you're doubling each time. Okay, so for every value, you're doubling it. Then what happens if we go in the negative direction? So let's say 2 to the power of -1, what's the same as? Half, because remember using this rule over here, I told you that most students will forget this. 2 to the power of -1 is the same thing as writing 1 over 2 to the power of 1, which is half. So, 2 to the power of -1 is half. Then what's 2 to the power of -2? A quarter, because it's 1 over 2 squared, which is a quarter. So it went from 1, half, a quarter. What's the next one? 1/8. Next one. So what's happening now? You're halving. So after the 0 line, so if you think about this graph here, ooh, now I lost myself. All right, here we go. Here, when we went in the positive direction, you're doubling itself. That's what the number 2 means. The number 2 means you're doubling it. Times 2, times 2, times 2, you're doubling. But then when you go in the negative direction, when x is negative, it becomes a fraction. Because it's a fraction, it's the inverse. So instead of doubling, you're now halving. It's like inverse of times is divide. So instead of times 2, you're dividing 2. That's why you're halving. So it halves and 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 it halves. Now, there's obviously a property here. So I've got my exponential graph. I know why it looks like that, because it doubles and then it halves and it halves and it halves. But there are 2 properties that you must know about exponentials. Name me one. Ben. Yeah, or not at x equals 0. At what 0? Y equals 0. Why is that? Because as you think about it, you can keep halving and it keeps getting smaller and smaller and smaller and smaller, but you can never halve a number that gives you exactly 0. That's why we say that there is an asymptote along this line, and this line is your y equals 0 line. Okay, x equals 0 is the vertical one. Okay, because x is always your vertical sort of, you draw it vertically. Yeah? So you got an asymptote. That's the first property. Asymptote at y equals 0. One more. What's the other one? One more obvious fact that we know. It is? No, oh, yes, all the y values are positive. That is something to pay attention to. That's true. But something else. Something that's even true for y equals 3 to the power of x, which your statement is still true. Y equals 4 to the power of x. There's something that they all have exactly the same. They all go through 1. Because we know anything to the power of 0 is 1. So they all cross through 0, 1. Okay, so those are your 2 properties. Why do I emphasize those 2? And I tried to show you in the last session that we had was you can change it moving left, right, up, down, and that only changes your asymptote if you're moving up and down. But if you move left and right, your asymptote doesn't change. Okay, you're not moving the graph, you're just moving the graph left and right, and it only changes your y-intercept or not. Okay, I'll go back to the GeoGebra so you do a nice recap or memory of what exponential graphs look like. So let's have a look. And I'll show you the left, right, up, down, and then if we have a bit of time, we'll go back to logarithms, and we'll start on some of the rules there. Let's go chapter 11, exponential graphs. Here we go. Bam, 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 bam. GeoGebra. All right, here we go. Can we bring GeoGebra into our exams? Maybe in year 12, some schools use laptops. They have a program that you can use. Wolfram Alpha, I think that's what it's called. If you guys ever heard of it. Some schools use that.
Our school's too nice.
I don't know. I feel like that's cheating. Apparently in that program, you can just type solve something and it just does the whole thing and it gives you the answers and steps and... Yeah, I don't know.
And our school's so nice to us.
Anyways, here we go. So I got a 2 to the power of x there. What I want you to see is what I've always taught you. If you move... Oops, not this one. Was it this one? No.
Yeah. No, it's P.
No, that's not what I want.
What do you want?
I want the up down.
That's D.
That must be D. Why can't I make it 0?
You should change it to typing.
There we go. All right, D. Let's do D, so. And D doesn't work. Do you know why?
You got the wrong equation.
Yeah, there we go. You know what? I'm going to change this so that it's easy to move.
You could have done that ages ago.
I should have done it.
But you just change it to typing numbers.
Does that work now? Okay, that's much better. Okay, so the red one was just so it stays static so you can compare and see what happens. Now notice when I put a D into it, I want you to look at what happens to the equation. So this is your equation. Blue, I'm just going to make it large so you can see. All right, here we go.
Oh, is it a dot time?
Yep.
All right.
So just like every other graph you've been learning, quadratics, cubics, exponential, not exponential, truncus, hyperbolas, they all follow the same drill that I've been teaching you. So I said, if you have a number that you're adding on, okay, that should be moving the graph up or down. That's exactly the same. So if you think about it, right now you got 2 to the power of x plus 2. It's like saying x squared plus 2. It's like saying x cubed plus 2. Everything that you've been doing with me before is the same thing. That plus 2 shifts the graph up by 2. Now remember the properties of the exponential. I said you have a horizontal asymptote, which was at 0. So if you move it up by 2, your asymptote now is at 2. That's why it never touches 2. There's an asymptote at 2. So that's why you need to know the properties. If you have an asymptote horizontally, you move it up and down, that's all it does. But you see, if I change it now, if I move left and right, it shouldn't change the asymptote. So if I move this back to 0, 0, I think this was, there we go. You see how I'm moving it left and right now? So I'm moving it left and right, and what I want you to see is the asymptote doesn't change. And it makes sense. Your y-asymptote doesn't matter because it's just left-right, so of course it doesn't change your y values. That's why it's still at y equals 0. So, how do you know if it moves left and right? It's always what you do with the x. If you think about what you're doing to the x values, and this is how I taught you with quadratics, I said that whatever you're dealing with the x, anything that deals with the x, so right now it's 2 to the power of x, but now it's 2 to the power of x plus 2. So this, if you want to know if you're moving left or right, I always said let it equal to 0. Remember that? So if I give you a quick example, remember with quadratics, this is what it would have looked like. You normally would have had y equals to x squared, and then if I gave you y equals x minus 2 squared, how I taught you was I said, whatever's in the brackets, whatever you're dealing with x, take that and make it equal to 0 and solve it. That will tell you if it moves left or right. Yeah? So what you would have done, you would have said, this is x minus 2. X minus 2 equal to 0. Solve for x equals 2. What does that mean? Positive 2 means to the right by 2. So that will shift the graph to the right by 2. And that was the same with any other graph I taught you. So let's say the square root function. It's root of x. So rooting, and what's your thing that you're playing around with is your x value. So if you change this and you said, all right, I'm gonna do now root of x plus 2, okay? Then what you're changing now is your x value. So if you wanna know, this is moving your left or right. So how do you solve for that? Same thing. Same drill as what I just taught you for your quadratics. You let x plus 2 equal to 0. You solve for x and it becomes x equals negative 2. What does that mean? That just means you're moving to the left by 2. So now this is no different with exponential graphs. So when you have 2 to the power of x, and all I'm changing is what you're doing to the x. If I do it 2 to the power of x minus 1, so if you want to know if you're moving left or right, just look at that. Whatever you're playing around with the x is your horizontal change or transformation. So if you want to solve that, find this out and say x minus 1 equal to 0, solve for x. It's positive 1, and that means, what does positive 1 mean? Yeah, to the right by 1. And that's exactly what this is doing here. See, if that's plus 2, x to the power of x plus 2, if you solve for it, means x equals negative 2. So it means it should be moving to the left. So that means if I keep increasing that c value, it should keep moving to the left. See, if I keep increasing that c value, it's plus 6, plus 7, and it's moving to the left. Whereas if it's the other way, if it's minus, it's moving to the right. See that? Okay, so it's the same thing that I'm teaching you guys. So what you do for quadratics is exactly the same for exponentials. The only thing you have to pay attention to are the two properties. They all cross at 1, okay? And when you shift it up, it obviously affects your y values and it changes the asymptote. That's the only thing you need to remember, yeah? Then you had your negatives. Remember there were two types of reflections. For the square root function, you could reflect it along the y-axis or you can reflect it in the x-axis. It's the same thing with your exponentials. If I want you to see here, so if I change, I'm gonna put this back to 0. Watch when I change this to a negative value. So a is this number here, the dilation 1. If I change that to a negative, okay, so if I increase it, it makes it thinner or wider, but then if I change it to a negative, yeah, and that makes sense. It's like your x squared. If you put a negative in front of a function, okay, negative square root, negative 1 on x, negative log, negative x cubed, it's reflection in the x-axis. It's like, this is your quadratic. If you put a negative x squared, it goes frown, happy face, frown. Same thing with exponential. If you put a negative outside the function, it changes all these y values to be negative. But if I switch it the other way around, if I play with the x, if I play with the x values now become negative. So watch what happens when I change the x, or if I do something with the x values. So this is going back to normal. There we go. And I think it was p. No, not p. Uh-oh. Let's go back to 2. B. There we go. Now B deals with your x values, and you can see as I increase it, sorry, if I just go back to the negative, there you go. When it's a negative x, so if you're playing with the x values, it affects your x values. All the x values currently now become negative. So it's positive x values, they become negative, so it switches. It's reflection in your horizontal, and that's exactly the same for every other graph you've been doing. Square root was the easiest one to see. Square root, if you put a negative in front of the x, it switches the other way. So if you remember with square root functions, which I'll quickly do here, this is your normal square root, root of x. If I did negative root of x on the outside, then it becomes this. If I did root of negative x, then it becomes this. And if I want it to go down this direction, it'll be negative of root of negative x. So what I'm doing there, that's what we did with square roots. It's exactly the same with exponentials. Okay, and that was the last exercise I left you guys with. You have to learn how to sketch and watch the properties and have to be able to do the algebra so you can solve for x and y intercepts. Cool? All right. So that's a quick recap there. Now, logarithms. You're going to copy these rules and we're going to practice some. Okay, I'll pick probably 1 or 2 and then we'll just practice them now. Yeah? Logarithms. So if you know how to times, then you have to learn to divide. If you know how to add, you've got to learn to subtract. If you learn how to do the power of, then you have to find the opposite, which is what we call logarithms. So if you do 2 to the power of 3 equals 8, then there has to be a reverse. There has to be an inverse operation to that. So it's called logs. So here we go. Hey, same example as I just said. 2 to the power of 3 equals 8. This is the logic. It's like saying, I'll do a comparison on the side so you can see. If I did 2 times 3 equals 6. Yeah, this is what you learnt in year 7. And then we started to increase it. So you learnt BODMAS or algebra. Right here is now 2 to the power of x equals 8. It's exactly the same thing as saying 2 times x equals 6. See, back in year 7, we would have taught you, we said, oh, well, we need to figure out that value. Some of you guys would have been like, oh, it's 3 because you knew your times tables. But we had to teach you a technique. And the technique was, if you times it by 2, you had to do the inverse, or undo the problem. And you said, well, opposite of times was divide. And you would have said, divide both sides by 2. That's how you first learned it. And you would be like, 2 cancels out with 2. But really, it's 2 divided by 2 becomes 1. So now you would say x equals to 3. Yeah, and that's why you know 2 times 3 has to give you 6. Now, it's the same thing over here. With exponential, you did 2 to the power of 3 equals 8. Now, we didn't know that. If we had 2 to the power of something equals 8, I know logically we know the answer, but if the number gets larger, there has to be a technique. So the technique is, well, how do you undo that problem? See, over here, you had an undo problem. You undid it by saying times, then it's divide. How do you undo an exponential base 2? And it looks weird. That's why a lot of students find it hard. It just looks weird, but if you understand it as the same concept over here, it's the same thing. To undo that base 2, and you want to get that x, it is called log base 2. That's all it is. Okay, so how I would write it mathematically is I'd say log base 2 of 2 to the power of x. Okay? Just like you did here, it was times 2 divide 2. Yeah, see, that divide is your operation. That log is my operation. That's divide 2, that's my 2. That's base 2, which is like saying times 2.
So does the log change? Does the bottom number change depending on what?
Yes, depends on what that number is. So if it's 3 to the power of x equals to 27, which I know is 3, if you want to undo that 3, it'd be log base 3 of 3 to the power of x. Okay, now, here's the thing. We know that we're doing inverses, they should cancel out. It's like saying this. X plus 3, opposite of plus 3, take away 3. And that still gives you the answer of x. True? If you had x times 2 and then divide 2, the answer should still be x. Then the same thing here, log 3, exponential 3 should still be x. Whoops. Okay? It should still be that. So what we can say here is if you can cancel out the 3 and negative 3, times 2 divide 2, you can cancel out log 3 base 3. If you do that, you can now say this is equal to x because you've cancelled out these two are inverses one another. The answer is still x. You can type this in your calculator if you want to. You can actually type log base 3 of 3 to the power of x and it will come out as x. Okay, because even if you type in your calculator like 3 times 2 divide 2 or 3 plus 2 take away 2, it's going to come out as 3. It's the same thing here. If you wrote log 3 of 3 to the power of 2, it'd still be 2. Okay, so they're just they're undoing each other. That's the same thing. The only hard part to it is visually, it looks weird because you're so used to symbols. You're used to having times, add, subtract, multiply. You know, it's sort of that sort of drill. So it's the same thing. Whatever you do to the left side, you do to the right side. See how over here you said divide 2, divide 2. I'm doing exactly the same thing over here. If you did log base 3 of 3 to the power of x on the left-hand side, then on the right-hand side, you should also do log base 3 of 27. Okay? That's what we can do here. Same thing over here. If I did log base 2 on the left-hand side, I would have to do log base 2 on the right-hand side. So this would now be, if I just rewrite it all again so you get used to this, so I'm saying log base 2 of the left-hand side, then I'm doing log base 2 of the right-hand side, just like you did here. Divide 2 on the left-hand side, divide 2 on the right-hand side. Same thing. Same as year 7 mathematics, yeah? Then I know log 2 and base 2 will cancel out and you get x is equal to log base 2 of 8. How do you know that that equals to 3? Now you have to use what you learnt in year 7, breaking into factor tree. If you remember factor tree, 8, you want to break it into its prime factors. Now we know that 8 is the same thing as writing 2 to the power 3. But let's say you didn't. You can break the 8 into 4 times 2. And that's a prime number. So now you're going to break the 4 into 2 times 2. So now you can say that's 2 times 2 times 2, which is the same thing as writing 2 cubed. Why do you want that 2 cubed here? Is because then rewriting this is the same thing as writing log base 2 instead of writing 8, 2 to the power of 3. And we know that these two are inverses of one another. That's why you get the answer 3. Okay, now I know your textbooks don't teach it this way. I'm teaching it this way so at least later on it'll make more sense in terms of your rules. Okay, so I'm just trying to teach you what you did in year 7 and what you're doing now is exactly the same. The only new thing is the operation looks funny. Okay, there's no symbols now. Your symbols, your letters. Does that make sense? Yes? Okay, let's do a couple of examples, okay? Let's have, actually not, don't worry about that. Let's go to this one. Same drill. I know the answer's 2. Okay, I know we all know the answer's 2. It's just like back in year 7 when we do 2 times magic number equals 12, and you would have been like, oh, I know the answer's 6. I don't want that. It's not trial and error anymore. We're now moving on to a technique. And your technique back then was if this is the x value, opposite of times was divide, and you would have said divide both sides by 2, because they're inverses, and 2 divided by 2 should cancel out to be 1, and x equals to 12 divided by 2, 6. Same thing here. Okay, so inverse operation of base 3 to the power, which is what? How do I get rid of the 3? What's the undo? What's the inverse operation? Log 3. So I'm going to log 3 on the both sides. I'm going to do log 3. So that's my operation. Log is my operation. 3, because that's a base 3, of 3 to the power of x is equal to, now what if I do to the left-hand side? I do to the right-hand side. So now I'm going to do log base 3 of 9. See, that's what I want you to see. It's exactly the same technique. You did divide 2, and I did log 3. Okay, you did divide 2 on the left-hand side, you did it on the right-hand side, I did the same thing. I did log 3, left-hand side, log 3, right-hand side. Okay? The nice thing about this is I know log 3 and the base 3 are inverses of one another. So they should cancel out, just like here. 2 times 2 and divide 2 are inverses. So they remove each other out. Yeah? It's the same thing, that's 1, that becomes 1, so that becomes 1x there. So you got x, 1x is equal to, now we're stuck here, we're like, all right, well log 3 of 9, I know the answer is 2, but how do you show that? It's the same thing as writing log base 3 of 3 to the power of 2. Okay, and we know log 3 of 3 are inverses of one another, so the answer is 2. Okay, that's the reason why it gets a bit tricky, because you're using letters to replace symbols. That's why it's tricky, but the concept's the same thing. If you can do the power of, there had to be an inverse to it. When you first learnt times, there had to be an inverse to that, which is division. When you first learnt addition, there had to be an inverse to that, which was subtraction. This is the same thing, no difference. Okay? Because once you understand that, then the rules will make more sense. When I show you the rules and where it comes about, it all makes sense why this works. Okay? All right, how do we feel with that? We've got a little time, so I'm going to just jump down. Okay, here we go. The reason why I'm saying this is because in your textbooks, they teach you to convert this, they call it converting to a log. You're not really converting, all you're doing is just doing left and right hand side, and it just happens to have a log. But what they want you to get used to is getting x by itself. So what they would say in your textbooks is they say you would write it as x equals 2. If it's base 5, you do log base 5, 25. A lot of kids will forget this. So what they do is they say the 5 goes to the bottom, and you got your 25 on the right-hand side. A lot of kids will try and memorize this. And if you want to change this back to an exponential, they say move the 5 over here. It becomes 5 to the power of x, 25. I don't like teaching that way because you're memorizing and you get confused by this. But if you understand it as balance in the equation, left and right, it's the same thing. Okay? So we'll start off today's session just getting used to converting these values into a log. Okay? Now let's have a look at some exercises. We go. Let's have a look at these ones here. These are some of your common values. I'll just take off. Oh, how do I take off the ink? Oh. All right, here we go. Normally there's a clean the screen button. Okay. Here we go. So in your textbook, this is what they want you to do. They just want you to convert an exponential to being able to solve for x, and you're meant to stop here. Okay, you're meant to stop here and just leave it there. Because they're trying to teach you to convert it from an exponential problem to a logarithmic problem. What I'm trying to teach you is that I want you to balance the equation rather than converting. It's not converting, it's just balancing the equation. Yeah? So that's what you're doing over here. That's how I'm teaching you to balance the equation. That's where that's coming from. You're doing log base 3 on both sides. And over here, they'll then ask you to evaluate. Same with every one of these. Every one of these, use your factor tree. Okay, use your factor tree. So with the 32, if you want to remove that log, you have to find something with a base 2. So how do you get 32? I can rewrite that as log base 2 of 2 to the power of 5. And conveniently, I know that log base 2 of 2 are inverses of one another, so now you can say that's equivalent to 5. Same thing with this one. 3 to the power of something. I want it to be base 3 because I know the log 3 and the base 3 will cancel out. So rewriting 81, I can write log 3 to the base 3 to the power of 4. Because 3 to the power of 3 is 27, to the power of 4 gives you 81. Again, logs 3's cancel out. That becomes 4. Now here's a tricky one. What about this one? Log 2 of 2 to the 0. Fantastic. See, 1, we knew from exponentials, how you can also get 1 is you can write 2 to the power 0, because we know 2 to the power 0 has to be 1. But the nice thing is you got the base 2. Log 2's cancel out, and you get the answer of 0. So one thing that you can take out of this is, anytime you do log something of 1, it has to equal to 0. Log base 3 of 1, 0. Log base 4 of 1, 0. Let's have a look at this one. What's log 2 of 2 then? The inverses of one another, what does that cancel out to be? 1. Not 0. A lot of students think it's 0. It's not. It's 1. Okay, it's like saying 2 divide 2 times 2 and then divide 2. They're just inverses one another. They cancel out to be 1. Yeah, so if you think about it, if I had 3 times 2 divided by 2. See, that's a times 2 and that's a divide. Even though you cancel it out, what you're really saying is that's a 1, that's a 1. That's why it becomes 3. It doesn't become 0, because if it came to 0, that would have been 3 times 0 is 0. So that's not true, okay? It's 1. Same thing here. Log base 2 of 2. They cancel out to be 1. How do we feel with that? Because I'm going to stop there and we're not going to go through rules. All I want you to be able to do, balance the equation, change an exponential to log, and be able to evaluate some of the easy ones. Factor tree. Cool? All right. Let's bring you to some of the page once I can get out of this. Or maybe I should read that letter. Yeah. Who do you take me for? All right. All right. There you go. Oh, there's not much. Oh, actually, I'll give you some of the ones I think you can do now. So A, B, you can do A, B, C, D. What else? Maybe I'll do this one. Let's try that one. That one. That one. Alright. We'll stop there for now. That should be enough the next 5 minutes. So those questions. 1 A, B, C, D. 3 A, B, D. E, G, I, K. I can't wait for the snow.